Welcome back, and for those of my students, I hope you've looked at this before the lecture. So today we're going to talk about multiplication division. I have a picture here of some multiplying cells, probably mitosis or something like that. So let's talk about the basic rules to start with. So if we have some variable, let's say it's a positive number for simplicity, we take x to some power and multiply that by the same number to a different power, and we just get x to the a plus b. The powers add. We can do negative powers, and this corresponds to 1 over, so division of the first power. And finally, we have a unit multiplication, so x to the 0th power is always equal to 1. As a simple example, so x to the minus 3 times x to the 5 is equal to x to the 5 divided by x cubed. And that's the same as x squared. And that's the same thing as x to the minus 3 plus 5. So everything's the same. So if we do powers of powers, or exponents is another word we use. We have that, let's just do one example. Minus 4x squared times y to the minus 3 all squared is equal to, well, it's this times itself. And so if you like, we could multiply all the corresponding terms twice. So this is also equal to minus 4 squared times x squared squared times y to the minus cubed squared, and we multiply the powers. We obtain that this is equal to 16, x to the 2 times 2, which is 4, and y to the minus 6, minus 3 times 2. So note, so this is where the multiplication comes in. This minus 6 is minus 3 plus minus 3, which is the same thing as minus 3 times 2. And so finally this is equal to, if I like, I can write 16x to the 4 divided by y to the 6. So let's give another example of where powers are useful. Is the binomial expansion. So the question we want to answer, so what's the problem? So we want to ask, what is a plus b to the n? So let's try, well, we know for small numbers of n. So for n equals 1, let me do this in blue. So for n equals 1, we get a plus b to the 1. It's just a plus b. For n equals 2, we get that a plus b squared is equal to a plus b times a plus b. And we know from quadratic lecture before, this is a squared plus 2ab plus b squared. But for once, let me do this in all its glory. We could have seen that this is a times this term, so this a squared plus ab plus b times this term, plus ba times plus b squared. But of course, AB is equal to BA, and so we get A squared plus 2AB plus B squared. So why did I do it in this way? You might notice that if we think of the possible, they're known as monomials, the possible terms, the coefficients of the various powers, for n equals 1, we get 1, 1 for A and B. And for n equals 2, we get under a squared, under ab, and b squared, we get 1, 1. That's these two terms, plus 1, 1 this way, these two terms, to give us 1, 2, 1. And similarly, we can do the same thing for n equals 3. We have that a plus b cubed is equal to a plus b times what we already know. That's a plus b squared. So if we do this the long way again, we see this is a cubed plus 2a squared b plus ab squared. So this is one extra a on this term. And we add on the same term, but with an extra power of b. And so when I sum them, I get a cubed plus 3a squared b plus 3ab squared plus b cubed. And we can see under this monomial format, where if I, for instance, drop the symbols, I can see that what I've really done is I've added 1, 2, 1 to 1, 2, 1 to get 1, 3, 3, 1. And so this was studied a long time ago by Blaise Pascal, at least you might have heard of this. Working this out, working out the coefficients of these monomials is known as evaluating Pascal's triangle. It is exactly starting with 1, which is the case n equals 0, then doing 1, 1, n equals 1, 1, 2, 1, so n equals 2, 1, 3, 3, 1, and so on. So these coefficients are known as the binomial coefficients. So knowing this, let's do a few examples. Let's try to expand 2x plus x inverse, or x to the minus 1, times y cubed. So we can see that what we want is the third row of the binomial coefficients, or the third row of Pascal's triangle. I'm going to call this the 0th row. I like to always rewrite it myself quickly as a little sketch. So what we get that this must be, well, we note down the coefficients first, and each term. So this is going to be my a, and that's going to be my b. So what we must get is 2x cubed, then is 2x squared times x inverse y. Then this one must be 2x times x inverse y squared plus 1 times x inverse y cubed. I edited my locations. And so this is some mess, which if I multiply out, I get 8x cubed plus 3 times 4 is 12, x squared times x inverse y, plus 6x times x to the minus 2y squared, plus 1 times x to the minus 3y cubed. And here, if I simplify, x squared times x to the minus 1 is just x, and x times x to the minus 2 is x inverse, x to the 1 minus 2. So our final answer is 8x cubed plus 12xy plus 6y squared over x plus y cubed over x cubed. So that's the section on multiplication. Let's move on to long division. Of polynomials. Note that as a definition, I've been using this already, but let's note that a polynomial, so definition, a polynomial of degree, another important word to know, of degree n, let's say in variable x, is an expression of the form an, these are some constants, x to the n plus an minus 1, x to the n minus 1 plus dot 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 all the way to a1 x to the 1 plus a naught, which is multiplied by x to the 0, where the coefficients just numbers, and for this to be a degree n polynomial, we say that the first coefficient, the highest one, is non-zero. Multiplying out is simple, e.g. x plus 2 times x plus 1 is equal to x squared plus 3x plus 2. But what if we try dividing? E.g., we know that in this particular case, x squared plus 3x plus 2 is equal to x plus 1 times something plus a remainder. And this something is itself a polynomial. Of course, in this example I've just picked, we actually know that the remainder is 0 and this something is just x plus 2. But in general, that may not be the case. So this is known as the divisor. What I'm dividing by, and this is the remainder. Let's do an example where the remainder is non-zero. So let's try to divide x squared plus 2x minus 12 by x minus 3. The method, so we write the big one we're going to divide, and we're going to divide it, so the divisor is x minus 3, and we're going to try to find this something which multiplies with this to give this up to some remainder. So I need to multiply x by x minus 3 to give me this top degree term. And I'm going to subtract that off, because I'm going to try and chop down this big polynomial into a bunch of smaller ones that multiply on with x minus 3. So this minus this gives me 5x. And I still have the minus 12 from the beginning. So I should have a plus 5 to kill off this lower term. And this gives me 3 as my remainder. So what we have is that our original polynomial is equal to x plus 5 times x minus 3, or the other way around. Let me write it in the same way as I did earlier. The divisor times what we figured out, but there's a remainder term. Alternatively, we can say that x squared plus 2x minus 12, all divided by x minus 3, is equal to x plus 5 plus 3 over x minus 3.